All right, so this problem says people buying food in a sealed bag at high elevations often notice that the bags are puffed up because the air inside is expanded. A bag of pretzels was packed at a pressure of 1 atmosphere and a temperature of 22 degrees Celsius. So let's say in Florida, it was packed in Florida at 1 atmosphere and 22 degrees Celsius. When opened at a summer picnic in Santa Fe, New Mexico, at a temperature of 32 degrees, the volume of air in the bag is 1.38 times its original volume. What is the pressure of the air? So Santa Fe is at a height and the pressure is lower. The pressure decreases exponentially. Yeah. So here the ideal gas law, PV equal to nRT. So PV divided by T equal to nR. So if the bag remains sealed, the number of gas molecules in the bag is constant. Okay. So this ratio P1 V1 or T1 equal to P2 V2 or T2. What this means is if you pack the bag in Florida, the pressure in Florida times volume in Florida divided by temperature in Florida equal to pressure in New Mexico or Santa Fe, volume, temperature. Okay. What is it that we want? Pressure of air. We want P2. So P2 is T2 over T1 times V1 over V2 times P1. What are the units for temperature? Kelvin. So as soon as you have the ideal gas law, temperature is in Kelvin scale. Okay, so the pressure in Santa Fe, T2 over T1 is 32 degrees Celsius is 305 Kelvin, and 22 is 295 Kelvin. V1 over V2. In Santa Fe, the volume is 1.38 times the original volume. So V1 over 1.38 times V1 times P1. So the V1 cancels. Okay, so the pressure in Santa Fe is 75% that of P1. P1 was 1 atmosphere, so it's 0.75 atmospheres. Okay. This says a cubic container of volume 2 liters. 2 liters is your bottle 2 liters?
This is half gallon, so yeah, about.
Yeah. So holds 0.5 moles of nitrogen gas at a temperature of 25 degrees Celsius. What happened to my water? What is the net force due to the nitrogen on one wall of the container? Compare the force to the sample's weight. Okay. So there's the volume, D. We'll call it length. Okay. Force is pressure times area. And pressure is nRT by V. Okay. So that's the force on the wall. All right, let's plug everything in now. N is half a mole. R is 8.314 joules per mole per Kelvin. Temperature is 298 Kelvin. And volume is 2 liters. A liter is 10 to the minus 3 meter cube. 1,000 liters is 1 meter cube to the power 1/3. So everything is in SI units, so the force will work out in newtons. Okay. 10 to the minus 3 to the power 1/3 is 10 to the minus 1. So that'll come to the top, it becomes 10. That'll make it 5. So force is 5 times 8.14 into 298 cube root of 2 newtons. Okay. Wow. 10,000 newtons. That's 5 times the weight of my car. On that wall. Hold up your drink. On the wall of your container.
How did you do
Did I do it right?
2-liter conversion?
A liter is 10 to the minus 3 meter cube. 1,000th of a meter cube. 1,000 liters is 1 meter cube. And then this thing to the power of 1/3 is 10 to the minus 1. That brings it to the top, that makes it a 5.
My brain is just confused. I'm used to saying meter cubed, so I'm trying to convert it in my head, and it's not working.
All right.
I mean, isn't it?
Okay, a liter is, okay, hang on a second. A liter is 2 liters. A liter is 1,000 centimeter cube. Okay, 2 into thousand. Centimeter is 10 to the minus 2 meters cubed.
Oh.
Yeah. That's pretty amazing. Yeah. So if you if you take that to space in your sealed thing, that should explode. Well, I don't know if it'll explode, but it has to be strong. What is the gauge pressure in a 25 degrees Celsius car tire containing 3.6 moles of gas in a 30-liter volume? What will be the gauge pressure if you add 1 liter of the gas originally at atmospheric pressure and 25 degrees Celsius? Assume that the temperature remains at 25 and the volume remains constant. Okay. So the pressure is nRT divided by volume. 3.6 moles. R is 8.314 joules per mole per Kelvin. Temperature is 298 degree Kelvin. And 30 liter. A liter is 10 to the minus 3 meter cube. So the pressure is, okay, this comes to the top, that becomes 10 to the 3. And everything is in SI units, so pascals. 3.6 into 8.314 into 298 divided by 30. And this is 1 atmosphere. So the pressure is 3 atmospheres. Okay. And what they ask you is the gauge pressure. So this is 3 atmospheres. Gauge pressure is the absolute pressure minus atmospheric pressure. So 3 minus 1 equal to 2 atmospheres. And 2 atmospheres is 30 psi, which is what the car tire pressure is in your cars. Well, it's slightly below 2 atmospheres. So what did you do? You went to Wawa and added 1 liter of air. Okay. So if you add 1 liter of gas originally at atmospheric pressure and 2.5, and the volume remains constant. Okay, so what we're going to do is, for part B, we're going to find N. N is PV times RT divided by RT. Okay, so there's the ideal gas law. We'll find out how many moles of gas did you add when you added 1 liter of air in your tire. And you added 1 liter of air in your tire, that's at atmospheric pressure, and so on. So 10 to the power of 5 pascals, 1 liter meter cubed. And 298 degree Kelvin. That's the temperature at which you added the air. So that's how many moles of air you added. Okay, that becomes 100. So that's 100. And moles will come on the top and everything else will cancel. The Kelvin will cancel. This is Newton per meter square and so on. Everything will cancel. Okay, 100 divided by 8.314 times 298. So when you added 1 liter of air at normal pressure, you added 0.04 moles of gas. Okay? And so you increase the number of moles from 3.6 to 3.64. The pressure increased by that factor. Okay? So the new pressure is 3.64 divided by 3.60 times 3 atmospheres. Okay. So when you filled up the gas, the pressure increased by so the new pressure is that. Okay. The pressure increased by 1%. All right. Some incandescent light bulbs are filled with argon gas. So argon is a noble gas. What is its RMS, VRMS for argon atoms near the filament, assuming a temperature is 2,500 degree Kelvin? So, okay, and VRMS is root 3 on. Okay, let me make sure of the expression. VRMS is 3 kT VRMS is 3 kT over m, or 3 RT over molar mass. Okay. I choose this one because this is easier to deal with. Okay. Okay, so argon, the molar mass you see is 40 grams per mole. Okay. So this is 8.314 joules per mole per Kelvin. The temperature is 2,500 Kelvin. Molar mass is 40 grams, 10 to the minus 3 kgs. Each gram is that many kgs per mole. So we'll make this 10 to the 3. That'll come up 10. It'll become 10 to the 6. Square root of that is 10 to the 3. Okay, so 10 to the 3 meters per second. 3 into 8.314 into 2.5 divided by 40. .25 kilometers per second. So those argon atoms are going at, they're going from here to the speedway in 1 second. You guys following this? Any questions so far?
One brief question on 38. Where did we get the M or mu?
No, M, that's the molar mass.
Oh, okay, my bad. From argon. Alright.
All right, so we'll do this. The partial pressure of carbon dioxide, we're using Dalton's law, in the lungs is 470 pascals, when the total pressure in the lung is 1 atmosphere. What percentage of the air molecules in the lungs is carbon dioxide? Okay, Mr. Dalton told us the partial pressure is Ni divided by N total. This is the fraction, the molar fraction, times the total pressure. Okay. So Ni over N total. The molar fraction is Pi over P total. 470 pascals, and 1 atmosphere is 10 to the power 5 pascals. So this is 10 to the power 5, 1, 2, 3, 4, 5. So 0.0047 is the molar fraction. Okay, and this is, to get in percentage, this is 0.47%. Yeah. So 0.5% of the molecules are carbon dioxide molecules. In this room, the fraction of carbon dioxide, percentage of carbon dioxide are 0.03%. So in your lungs, that's 15 times greater. So this is when you're getting ready to breathe out. Okay, the blood has exchanged the oxygen, carbon dioxide with the air in the lungs, and now you're ready to breathe out. And again, how does this happen? So Okay, here's carbon dioxide in the capillaries. Okay, here is your alveoli, and you saw that when you breathe in air, this was only 0.033%. And this is essentially, well, the carbon dioxide concentration is much higher, and it'll diffuse here. And then the carbon dioxide. So for diffusion to happen, for you to get rid of carbon dioxide, the concentration in the blood vessel has to be much higher than here. Okay? And that's how it happens. Okay. How much heat must be added to raise the temperature of 1.5 moles of air from 25 to 33 degrees Celsius at constant volume? Assume the air is completely diatomic. Repeat the same problem for the same number of moles of xenon. For A, CV, the number of degrees of freedom is, at room temperature for a diatomic molecule, the number of degrees of freedom is 5. CV is 5/2 R. For part B, xenon is, what is xenon?
131.2.
Yeah, so it's a noble gas, and the number of degrees of freedom is 3 at all temperatures. It's 3/2. Okay. So for A, QV is NCV delta T. N is 1.5 moles. CV is 5/2 R. And the rise in temperature is 8 degree Kelvin. All right, so 249 joules, and for part B, instead of 5/2, you'd be multiplying by 3/2. So divide this number by 5 times 3. So this divided by 5 is 50, times 3 is 150, 150 joules. So for xenon, it'll work out to 150 joules. Okay, so you see it's much easier to heat xenon than air. Beth here is falling asleep, so we'll do one more problem. I'm just picking on you. You're easy to pick on. All right, do you want to do deep space problem? All right.
What a funny question.
What a funny question, yeah. All right. In deep space, between galaxies, the density of molecules, which are mostly single atoms, can be as low as 10 to the power 6 atoms per meter cube. What is the density in this room? So here's a meter cube. 1 mole occupies 22 liters. and 1 meter cube is 1,000 liters. So 1,000 divided by 20 is 50 moles. 1 mole is 10 to the 24 molecules. 50 times that is 10 to the 26 molecules. So in this room, there's 10 to the power of 26 molecules per meter cube. In deep space, that's 10 to the 6 atoms. So the density is about 10 to the 20 times smaller. Okay? And the temperature is a frigid 2. What is the pressure? Okay? All right. So part A, the pressure is NKT divided by V. So N over V, KT. They give us N over V is 10 to the 6 per meter cube. K is 1.38 times 10 to the minus 23 joules per Kelvin, and the temperature is 2.7 Kelvin. And the pressure works out to that's 10 to the minus 17. So pascals. 10 to the power of 5 pascals is 1 atmosphere. So this is 3.73 into 10 to the minus 22 into 10 to the 5 pascals. That's 1 atmosphere. Okay? So the pressure is a billion trillionth time in this room. What is the volume occupied by 1 mole of gas? Okay, so volume is nRT divided by P. Okay, I will go to the next page. So volume is nRT divided by P. N was 1 mole, 8.314 moles per joules. The temperature in deep space is 2.7 Kelvin. And the pressure we calculated was 10 to the minus 17 Pascal. So the volume would be, this would come to the top, that would become 10 to the 17. So 8.314 into 2.7, 3.73 into 10 to the 17, and this will come out in meter cube. So one mole on Earth will occupy this much volume. We're going to take it to deep space and see how much this will expand to. Okay? Meter cube. 6 into 10 to the 17 meter cube. So we'll make this 10 to the 15, cube root of 10 to the 15 is 10 to the 5, cube root of 600. So 8.43 into 10 to the power 5 meters cubed. Okay, so it'll be a cube of that length. Okay, and 10 to the power of 3 meters is a kilometer, so 843 kilometers cubed. So this much gas. Now imagine 843 kilometers is from here to Atlanta essentially. This gas will expand a volume that way. All right.